Hi, I wanted to share the research update from the 2019 conference for those of you who were unable to join us in Colorado Springs. Just as a quick reminder, here are the 5 groups of conditions that we're interested in and dedicated to, 5 chromosome 18 condition groups. And I'm going to talk about 3 different things. I'm going to quickly go over the current projects that we're working on, as well as our strategy for treatment development, and then just a reminder of some of the resources we have for you. As a reminder, our goal is to make the chromosome 18 conditions the first treatable chromosome abnormalities, and by that we mean self-sufficiency. So what we're thinking about is for parents who, when you pass on, are you worried about your kids with typical chromosomes and how they get by in life, and are they going to be okay? No, you know they'll be okay. They'll get by. They'll do just fine. Well, that's what we want you to believe and know for your kids with chromosome 18 abnormalities. That's called self-sufficiency. We want them to be able to be self-sufficient. When we go to Washington, what we tell lawmakers is we want to make our kids ineligible for SSI. Wouldn't that be wonderful if they could be independent and we didn't need to worry about government benefits and who's going to watch after them? So that's our goal. It's a big, hairy goal. But if you don't have a big goal, you're never going to get there. So that's what we're working toward, and that's what I wanted to share with you today, our progress and our incremental progress that we're making on that front. So first, the current project status regarding all conditions. We recently completed a seizure survey, and a report went out to all the participants. I did a YouTube video explaining the results, and we are working on a paper to be published in the literature. With regard to tetrasomy 18p, we did a survey and a study on low bone mineral density, and that article has been published. And here's a picture of Dr. Morer showing the poster he did with these results at the Pediatric Academic Societies last May. As I said, the publication is out, and what we want to do now is follow up on treatment, because vitamin D and calcium supplementation did help. And so if anyone has follow-up DEXA scans or other data that tells us about changes in your bone mineral density, please let us know. We're collecting that data all the time, and we're always interested in hearing from you. In addition, with regard to tetrasomy 18p, families last year were very concerned about constipation, feeling like it was completely not only common but affected everyone. So we did a survey to find out how many were affected, how they were affected, and what treatments helped and what didn't help. And that information has been shared with all the participants. I believe that was back in March we did that. And the management guides were updated, and very recently those results were shared with all the members of the Chromosome 18 registry. So you can find out what we learned about constipation in tetrasomy 18p. Also, current projects with 18p, people with 18p deletions, and of course this would include people with ring 18 who have 18p deletions as well. And I know this is a mess of acronyms, but there's 3 things. That's the point here. 3 items, and I'll go over each of those. I hate acronyms. So anyway, the first one is spinocerebellar ataxia type 28. The gene for this is on 18p, and the gene is called AFG3L2. And this is a condition with an age of onset between 3 and 60 years of age, so a wide range of onset. Average age is 24 years, though, so this is an adult onset condition for the most part. It mostly involves incoordination, so walking incoordination, and in particular, speech articulation problems, so ataxic dysarthria. So not just speech that's hard to understand, but hard to understand in a very specific way. So we were concerned that people with 18p deletions may be in fact at risk for this, and we wanted to know if any had been diagnosed with it, if any had the first signs and were looking for first signs. So what we did last year at the Chromosome 18 conference was we did video tapes of a group of people with chromosome 18 conditions, who asking them to repeat words and say various things, and we had those analyzed by our speech therapist. And just for those of you who participated, we also did some recordings of people with 18q-, just so our speech therapist wouldn't always know if this was really a person at risk or not. So we threw in some people not at risk for this, just to sort of keep them honest and make sure that the data they described was accurate about those with 18p-. And here's what they found. So in those people with 18p-, so to explain the strategy here of how we analyze the data, we think the gene, the AFG3L2 gene, is responsible for this condition. Some people with 18p- have deletions that include this gene, and some people have deletions that don't include the gene. People whose deletions don't include the gene have 2 copies of that gene. So right here, there were 6 people in that group, and the assessment by the speech pathologist was that 4 had normal speech and 2 had spastic dysarthria. Hard to understand speech, but for a different reason. In the group that had 1 copy of the AFG3L2 gene, so they are at risk for this condition, there were 14 people, and 10 of them had normal speech, and 3 had flaccid type of dysarthria, sort of sloppy, low muscle tone type of dysarthria, and 1, in fact, did have ataxic dysarthria. So this isn't a very big group of people. We got more videos at the conference this year in Colorado Springs. We're mailing out our iPad, and we need a good microphone, and we need some consistency in the recording, so that's why we're not asking people just to record something on their phone and send it. We're sending out our iPad so we have some more consistent sort of data for the speech pathologist to review. If you are concerned that your child or young adult really with 18p has speech that is changing over time, and they may in fact have this issue, please let us know, and we'll get you on the list to send you the iPad and get a recording of your loved one with 18p- speech patterns. So that's one of the things happening with regard to 18p. Also, as you know, for quite a long time, we have been looking for first signs of facioscapulohumeral dystrophy type 2 caused by the SMCHD1 gene. The age of onset is usually before age 20, but it can be much earlier, but tends to be in the teens. And this is progressive muscle weakness that's asymmetric, so one side of the body is affected more than the other. And it often begins in the face or shoulders and upper arms. And so this very same video assessment had some tasks we were asking the participants to do, like smile and grimace and lift your eyebrows, that sort of thing, pucker your lips. And so those videos are being, same exact videos, are being scored by neurologists to look for first signs or early signs of facioscapulohumeral dystrophy type 2 or FSHD type 2. So that's a project that is ongoing. Then there's another gene on 18p, DLGAP1, and in the mouse model, it's been found that mice with the deletion of this gene have social interaction deficits and communication deficits, so sort of like maybe autism or an obsessive compulsive type behavior. This gene's been linked with, in typical populations, been linked to obsessive compulsive behavior. So we want to look for that in people with deletions of this particular gene. So that's an area of special interest at the moment. And now moving on to 18q-, with regard to those people with TCF4 deletions whose 18q- includes the clinical features of Pitt-Hopkins syndrome. We recently were part of an international collaborative group working on the diagnosis and management paper of Pitt-Hopkins syndrome. So that came out, I believe it was in November. We're also working with Steve Haggerty's lab at Harvard. A paper on that preliminary work has been drafted. And the study we've been trying to get going involved a wavelet, which that was the name of the particular device. It was like a Fitbit or an Apple Watch, and it would help us measure sleep and hyperventilation. That company, we found an investigator who was really interested in taking this on, and then the wavelet company got sold to another company who really wasn't interested in research data. And so we're sort of back to the drawing board with regard to devices, but we are working on this. We think that actually pretty much everybody with a chromosome 18 abnormality has atypical has atypical sleep. And so we're using this as a small prototype sort of study with those with TCF4 mutations, to see what kind of data we can get and see if it's useful, and then we'd like to expand to all the other conditions. So everybody stay tuned for this, because we think that improving sleep improves all aspects of your life, and so we want to know who has sleep issues and who doesn't, and what kind of sleep issues they are. So this is sort of a pilot project for sleep. So also with proximal 18q-, we continue to collect medical records, and we're looking for people with really small deletions to help us identify which genes are key with regard to that. And actually we've been finding more and more people with proximal 18q deletions recently. With regard to distal 18q deletions, we're really interested in identifying the dysmyelination gene, and I'm going to talk a little bit more about that later. And the NETO1 mouse, the knockout mouse, we're analyzing the data about behavior deficits and learning deficits in that particular mouse. So NETO1 is a gene that we think is important in the distal 18q- region. So those are ongoing projects. And then with regard to trisomy 18, we have a new collaboration that's just starting with Jason Seltzer's lab at Cold Spring Harbor. We're about to send him some cell lines with trisomy 18 cells, and he's interested in trying to shut down the extra copy of chromosome 18 and find out how that can be done. And so we're excited about that, and so that's a new collaboration. And one more thing I wanted to talk about, which is not really it's not at all our data, but it's new information on trisomy 18. And so this is a study that just came out, I think it was May of this year, and it looked at the surgical outcomes for heart surgery in infants with trisomy 18 and 13. And so this graph is from that paper, and so I know it's a messy graph. I wouldn't normally do this kind of graph to you in a talk, but this is from the paper. So what I want you to look at first is the axis over here. This is the number of surgeries, the number of cases that they had. Over here, it's different years from 2010 to 2017. And so the trisomy, the bars in blue are the number of trisomy 18 cases. So you can see here the number of cases that they had over the years. That included 304 patients. This was data collected from 87 centers. And the blue line is the mortality. And so on this axis over here is mortality. So what you want to see is mortality going down as more and more centers have more and more experience doing heart surgery on babies with trisomy 18. So if you follow this blue line here, you can see that mortality is going down, so surgeries are improving, and babies are living longer as a result of having the surgery. So we thought that was important information for our trisomy families to have. And over half of these surgeries involved a VSD repair. So the reference for this article is shown at the very bottom, or let me know, we can send that to you if you need to share that with your physicians. So moving on from our current projects, those are the things we're working on at the moment. And I wanted to share our strategy for treatment development. Where are we going? How do we see this in the future? So, of course, our goal is to help people with chromosome 18 abnormalities live independently directed lives, which, as I said, is a great big goal, hairy goal. And so what does that involve? That involves a lot of things. It could involve improving working memory, improving reaction time, attention, focus, anxiety, depression, behavioral regulation, all kinds of things. This is just a partial list of the kinds of things that could be improved, or depending on which condition, might need to be improved in order to help people with chromosome 18 conditions have independent lives. But our problem is these are kind of hard to quantify objectively, so that's one of our challenges. But before we can even work on that, we have to really describe the conditions. So our overall strategy, and we've said this over and over, has three basic components. This is what we've said for years and years that we're working on. First, we have to define the characteristics. We have to understand the conditions. Then we have to identify which genes are involved in those outcomes, and then change that gene action. So here's our path. This is what we've been working on for a long time. And with regard to defining the characteristics, we've actually made a lot of progress. When we started, the descriptions were broad mouth, low set ears, things like that. The facial characteristics. There really wasn't much information about outcomes and how they do. And so we've been learning a lot about that. Syndrome descriptions are on the Chromosome 18 Registry website. And over those years, we've published over 60 scientific publications that are in the literature. If you want a copy of any of those, let us know. And all that information was recently synthesized into management guides, so it's all reorganized, we hope, in a way that your treating physicians could use. So there's a cover page, which is just the 60-second summary. So somebody who's just a consultant, your dentist or ophthalmologist, somebody who just wants a quick overview of what the heck is this anyway. And so that's what the 60-second summary is. But the following pages are more detailed pages that your pediatrician or your primary care physician may want to use as a guide, depending on what stage of the individual's life they're interested in. It's organized sort of by what you need to do at a diagnosis, what you need to do with the newborn, and what's ongoing management sort of issues. So the management guides are published on our Chromosome 18 clinical research website, so you can get a copy of those. But that's not all. We are still trying to track outcomes, learn what happens to individuals with chromosome 18 abnormalities over time, not just as they become adults, but learn more detailed information about them as children and how they develop. And part of that is to obtain or devise some clinical endpoints. And so I'll talk more about that as this continues. So the outcomes really are lots of different things. It could be just developmental trajectory. How quickly do they learn to speak? How quickly do they learn various things? What are their milestones? When are they achieved? Natural history. This is sort of a big umbrella description of really all of these outcomes. How do people change over time with these conditions? And we also want to know about the effects of treatments. So any standard treatment, growth hormone treatment, treatment with calcium and vitamin D. What are the effects of these treatments and how do people do with them? Also, we're interested, as I've already said, adult onset conditions. The two listed here are the two that I talked about with regard to 18P minus. And we also want to know what unique aging issues do they have. We have no idea. Our cohort is pretty young, so we're following them for their lifetimes to learn about if there's any conditions that are treatable that are more common in this group that we need to make sure that treating physicians and families are aware of, so you keep your eye out for any of these that might develop. So these are the outcomes we're looking for. And I wanted to show an example, completely hypothetical, made-up example of why natural history is such an important part of what we do and why we want to keep track of how people are doing over their lifetime. So this is a completely hypothetical, made-up illustration. So here we have 6 people, and here's their data for 6 different people for some biomarker. This could be the level of something in the blood, or it could be height, it could be weight or whatever. In this case, here's the level here, and in this particular case, higher is worse. And in this bracket is the normal range. So a typical group of people would all have their little red dots somewhere in this range. So in our group of 6 with a chromosome 18 condition, 1's in the normal range and 5 are above the normal range. And so imagine we developed a treatment. And so we gave them all a certain drug that we thought would help with this particular condition measured by this particular biomarker. So we give them, this is the start of drug treatment, and then we measure that same biomarker at a later time. And so here's the post-treatment data. And boy, what we'd say when we look at this is, I don't think this works so well. Everybody got worse. And so maybe this isn't such a good treatment. But how do you really know? Well, one way you would really know if this is not a good treatment is if you had a placebo group, a group that didn't get treated. And those are shown with the black lines. Look at those black lines. They go up much faster. So in fact, the people treated, they got worse, but they didn't get worse as fast. So in this case, our treatment maybe wasn't perfect. It didn't reverse the course of the disease. It didn't stop whatever it was, but it slowed it down. So it's better than nothing, and nothing is shown by the black lines, the placebo. So that might be a sugar pill. It might just be no treatment. So the problem with this strategy, and this is what how most drugs are studied. There's a group that gets the drug and the group that doesn't. But that requires a really large group of people. You need people who are treated and not treated. We have ultra rare conditions. So having an untreated group is a luxury we don't always have. So what we do have is a lifetime longitudinal study that we're conducting right now to gather all this data from people. And so what if this is what we had? What if we had the data? Here's our starting point data, but what if we had data we gathered before this trial even started, years before this particular drug was even invented? And you can see that, look at the trajectory of this person, for example. They should have been way up here, except the drug put them down here. So in this case, we'd say the drug, this is what would help everyone be treated, not have a placebo group, and help us understand if the effect of this drug was in fact helpful. And this is called natural history data. And this is what we spend a lot of time collecting. We don't always know exactly what our biomarker is going to be. In fact, the natural history data helps us figure out what some of those might be, fine-tune them. So that's why we're always doing surveys, asking for more information, because this is all part of natural history data that's helping us position ourselves for when there is a treatment, we'll be ready to do a treatment trial that could involve everyone who's eligible and not have to have a placebo group. So that's the strategy for that. That's why we're always asking you for more information. So, natural history data, as I said, it could be all kinds of things. It could be just simple height and weight or blood tests or about speech development and how it's changing over time. It could be something simple as counting the number of seizures or reaction time, which I'll talk about a little bit more later, or behavior measures. And again, just as a reminder, here are the things that we consider obstacles to independence that we're looking for. And so our clinical endpoints might be, generally are improvement of the disease, but they need to be objective measures. So they need to be biochemistry measures, so blood or urine levels. They could be physiological measures, so a reaction time or an EEG or an ABR. I think you probably all have experienced those things. Or they could be anatomical changes, so it could be height or it could be a change in an MRI scan. So those are all clinical endpoints that we might want to measure for their effects in response to treatment. And then there are surrogate endpoints. So surrogate endpoints are faster and easier to study. They have to correlate with disease, and they have to be established long before a drug trial. So they're part of the natural history study. And excuse me, I'm recovering from a cold. I'm sorry. Suddenly have a tickle that won't go away. And I long ago decided I'm not trying to make these perfect. I'm just trying to get them done. Otherwise, if it needs to be perfect, you'll never see this. So, so pardon me. Again, surrogate endpoints are the kinds of things that we discover during the natural history phase, which is what we're all about all the time, actually. And so a clinical endpoint might be, for example, improvement in a disease, so reducing ADHD, for example, or improve learning ability. And a surrogate endpoint might be a physiological measure that correlates that, so a change in functional brain imaging, for example, something like that. So here's an example. We think that improving myelination, for example, would lead to improved nerve conduction velocity, which would improve your reaction times, which would, at least in the mouse, it improved emotional memory in the mouse. Maybe in a person, it might be other kinds of memory. So this is a hypothesis that improved myelination might improve nerve conduction velocity, which would improve reaction time, which it would improve memory. How do you measure those things? Well, you can measure improved myelination with an MRI scan. You can measure improved nerve conduction velocity with transcranial magnetic stimulation. And we've actually done a few of those in the past. You can measure reaction time with the finger tap test and emotional memory with cognitive testing. Some of these measures, outcome measures, have issues. MRIs are very expensive, in part because people all need to come here for the same MRI done on the same scanner, analyzed with the same software. That makes it very expensive to do and time-consuming, and it's a hassle for families to come for 2 different MRI scans all the way to San Antonio. So that's problematic. The increased nerve conduction velocity, which can be measured by TMS, is also, for the same reasons, costly. I think it's less well accepted and well defined. And cognitive testing is less accepted maybe by the FDA, which of course is where who's got to approve this. And it's not as sensitive to really fine changes, and so and also it needs to come to San Antonio, have this done by the same person doing the same evaluation. So again, it's a little less feasible, and that leaves us with the finger tap test, which we think would be a correlate. So it's a pretty easy test. We've been gathering this data now for 2 years at the conference. It involves a little board with a counter on it, just like the counter they use when you're going to a concert and somebody's counting the number of people going through the door. This counter is attached to this little board, and in this picture you can see the index finger of Bridget's left hand on the little clicker device, and we ask people to hold their hand flat on the board, press down as many times as you can in a certain period of time. And people who have delayed myelination, so people with distal 18q minus, have much slower reaction time, and they cannot press this nearly as fast as a typical person. So we've been, like I said, we've been collecting that data last year at the conference, this year at the conference. We're getting some of the same people so we can see if there's changes over time, measure consistency. This is a pretty easy, straightforward, low-cost thing to do. We theoretically could mail this out and have somebody videotape their child doing this, so we could collect even more data. So this is the strategy we're taking as our surrogate measure of myelination and reaction time. Again, a reminder of these are the things we're looking at and that are important to us to try to change, improve. And just to recap our strategy for treatment, so far we've been talking about defining characteristics and the syndrome descriptions, management guides, measuring outcomes, clinical endpoints. Those are all defining characteristics. The second part is identifying key genes, and we do that with our gene dosage map. Here's a partial screenshot of part of the gene dosage map. I've done a couple of videos on how to use the map, how to look it up, and what I do is keep up with the literature on every single one of the 263 genes on chromosome 18, and every single day I get updates from the NCBI, from PubMed, with any new publications having to do with any of the genes on chromosome 18. If anything if anything is published that's relevant to changes in number of copies of the gene, so how it might affect someone with a deletion or duplication of that gene, then I update the gene dosage map. And so it's updated continuously. And like I said, there's information how to look that information up. So far, just to quickly summarize, with regard to deletions, there are 12 regions on the map identified that are associated with specific features of someone with a deletion. The gene isn't identified, but the region is narrowed down to a small region. And 15 genes are identified as playing a role in the characteristics of people with a chromosome 18 deletion. So far, of the 263 genes on chromosome 18, only 23 have absolutely nothing known about them. And so I can't even hypothesize about their role, but that means the vast majority of genes, and like I said, there's 263 and 15 are identified. So as we've been saying for many years, we had hypothesized early on that only 10% of genes were going to be key. And so far, that seems to be holding up as we actually learn some information about the genes. With regard to duplications, that's much more problematic. There are fewer people with small duplications. The mouse models for duplications are not as robust. And so with regard to duplications on chromosome 18, we only have identified 2 small regions associated with features and 1 gene for sure. And 109 are unknown with regard to their role in a duplication. So there's much less information about the effects of a duplication of a gene. But, like I said, they get updated all the time, every day. I am looking up papers and keeping that updated. So we've made a lot of progress in that regard. The next item is changing gene action. And so we're actually starting to move forward on this as we figure out some of the key genes. And that's what I'd like to talk about next. So here's our current strategy. We have some pilot funding to begin this. It's now funding is finished, and so it's sort of sort of kind of on hold. We're kind of doing a few little things as we can, but it's kind of at a standstill at the moment. But here's what our strategy. We do have a few people with mosaicism for chromosome 18 conditions. So that means that some of the cells in their body are normal and some of them have a chromosome 18 condition. It could be tetrasomy, could be P- or Q- or trisomy or 18Q+, or any of the conditions. But we do have some individuals that we've enrolled who are mosaic. So what we can do is we take a skin sample, very small, little, smaller than the head of a eraser skin sample from one of these individuals, grow up the cells, and then we can, what we call subclone, so separate out the cells, the typical cells from, in this case, the 18Q- cells. And this is just an illustration about 18Q-, but as I said, it could be any of the conditions. So we separate out the cells. So we have one flask or many flasks with normal cells and other flasks in the incubator with 18Q- cells. Then what we can do is use the CRISPR technology, these are molecular scissors, to delete one specific gene, a candidate gene that we think is responsible for a specific condition, an 18Q-. And then we ask, how do these cells behave? In this case, if this gene is one of the key genes, this cell now behaves, maybe grows similar to, or whatever measure we're looking at, similar to the cells with 18Q- and is no longer behaves like the normal cells. So then we would know, aha, this is a key gene. And with CRISPR technology, we can delete more than one gene if that's what's required to make the cell behave in the same way that an 18Q- cell behaves. So the next thing is, when we find a key gene, we can make a mouse model. So what you do is you use the same CRISPR technology in an embryo, in a single cell, in a fertilized egg of a mouse, grow that up into an adult mouse, and then create a whole colony of mice that have this single gene deleted. Then we say, okay, is the behavior in this mouse that we're studying, is it the same as the behavior or the condition or whatever in the people? So we ask, does this gene do the same thing in the organism as in the mouse as it does in the people? And if it does, and of course that's a big if it does, then what we can do is then begin some assays to look at drugs. And there are core facilities. We have one here that has thousands of drugs, many of them already approved by the FDA, but didn't move forward. They were approved because they weren't toxic, but they weren't developed by the companies because they didn't really improve the condition they were developed for more in an improved way from what was already on the market, or they made no difference at all. So anyway, they didn't move forward, but they passed the initial toxicity stages. And plus there's new chemicals developed all the time, and so there's thousands of these chemicals. These are all done in robotic systems. You take your cells and you have little bitty wells in a dish, and you're growing the cells, and in each little well with cells you put a different compound, and you see which compound makes the cell with the 18Q deletion now behave like a typical cell. So that screening can be done. And if you find a compound, then you test it in the mouse. If it works in the mouse, then you move on to people. So that is the strategy. It's a very, very long road. And excuse me, another tickle. But that's the road that we're on. These are all very doable steps. We just don't have the funding at the moment to really pursue those in the way we'd like to. And the reason this is important, and the reason we're talking about myelination, is for the following reasons. First, we think myelination has behavioral implications. Improving myelination, we think, can improve reaction time, but it may improve ADHD, it may improve learning, it may improve the things we care about. At the same time, this is something that would have physiological outcomes that change. So really concrete, definable outcomes that are improved if we improve myelination. And in fact, it may in fact have anatomic outcomes that can be visualized on MRI or something. So these are not just behavioral, but physiological and anatomic outcomes that could be measured. Those are the things that make it saleable or appealable or whatever, fundable potentially to the National Institutes of Health. So we can approach this problem because we have more concrete physiologic and anatomic measures of improvement. But the other reason, beyond being able to get NIH funding to support this, is improving myelination may have implications for helping people with multiple sclerosis or potentially even Alzheimer's. So the market for this treatment and the interest in this might be bigger than just 18q-, which is part of what might make the NIH more interested in it. In fact, one of the recent grants that we wrote to the NIH came back with one of the main criticisms being that it only concerned 18q-. Well, of course it did. That's what we do. But the NIH is not interested in 18q-, but they are interested in myelination because of its potential for understanding multiple sclerosis, Alzheimer's, and other diseases of the brain. So that's why we're focused on myelination as our entry point. So let me show you kind of where we are in this path. So we know for sure that if you have a deletion of 18q of a very specific region, that you have delayed myelination. We don't know exactly which gene or genes in that very small region cause dysmyelination. That's what we're working to prove. And once we prove that, then, as I've just talked about, we can look at potential treatments. And then when we have potential treatments that improve myelination, we could look at the population bigger than 18q- that it might affect, that this drug treatment might affect. So this is what the registry needs to do, and this is what your funding needs to do, is help us move down this path. This is the part we care about, the part that appears to only be 18q-. When we figure out which genes are responsible for the dysmyelination of the brain in people with 18q deletions. So we've got to identify those genes and start getting the first steps. And once we get those first steps, then we can apply for funding from the National Institutes of Health. But the other part you need to remember is, if you write a grant to the NIH, it's going to be, even if it's approved on the first submission, which doesn't normally happen, it still takes 11 months before you would get any funding. So just because you can write an NIH grant doesn't mean you're going to get it, and doesn't mean and it definitely means it isn't going to happen soon. So the registry funding needs to actually fund part of the early NIH work. But an NIH grant could help us identify compounds that actually improve myelination. And if we can do that, identify some compounds that could move forward, that's the point where we could interest some venture capital to partner with us to move this drug treatment forward. And because they could be interested in the potential, they don't care about 18q-, but they might be interested in MS or Alzheimer's or other brain myelination issues. And so if in fact we do develop a drug that helps with 18q-, and by the way also helps people with MS, that could earn a lot of money. And as an example, the Cystic Fibrosis Foundation was instrumental in the development of the first treatment for cystic fibrosis. And in the first year that drug treatment, Clypco, was on the market, the Cystic Fibrosis Foundation earned $317 million in royalties. What does that mean for us? That means that kind of money could help us fund trisomy 18 research, 18p minus research, tetrasomy 18p minus research, research on any of the genes on chromosome 18. That's the kind of money that could help us do all the things we want to do. And so the key part is we need to figure out exactly which genes are responsible for myelination, are responsible for the delayed myelination in people with chromosome 18 deletions, and we need to be able to fund the first steps in identifying potential drug treatment. But this is the path we're on. This is why we're really focused on 18q minus and myelination, because we think this is our path to the kind of money we need to help and make inroads on all the conditions. And not to mention, if you do this in one, then people believe you can do it for another. And so money from the National Institutes of Health and other foundations start to believe in you. And because we have already done it, they think we can do it again, or they know we're going to do it again. And so this is our initial strategy for moving research forward to help everyone with the chromosome 18 abnormality, regardless of which abnormality it is. So, now, in conclusion, just to remind you about some of the resources available to you. Quickly review. The Chromosome 18 Clinical Research Center collaborates with a large group of investigators. Myself and Dr. Hale lead the group, and all these people from all these various medical specialties here, they're all volunteers at the moment. There was a time when we paid part of many of these people's salary, and we were getting a lot of papers written and doing a lot of work. Now it's a matter of them volunteering because their salaries are paid to do other projects or to see patients, and so we're trying to get their spare time, of which they really don't have any, but they've been working with us a long time and are really committed to this project and to helping all of you. And so it's an amazing group of people, and we appreciate all the hard work that they put in their spare time. We also have a great staff. We have 2 people in our administrative office who help us. 2 people in the laboratory. Elizabeth Cody actually work for one of our collaborators who's out of funding at the moment. So Elizabeth is on hiatus, but most of the lab work is done by Patty Hurd. And the rest of the research team, not in the lab, include Annis Hill, Mimi Hasse, David Rupert, Bridget Swallow, and Courtney Siebold. And these people have really dedicated their lives, their careers, to helping you. I think everybody who has worked for this team for at least 15 years. And so that's a significant amount of time. They really are the experts on the chromosome 18 abnormalities, and they really, really care about helping you. So I hope you really appreciate all their hard work and their dedication, and them dedicating their careers to helping you. Here's what they do. These are our core activities that your funding helps to support. Of course, we have a DNA and cell bank from all the blood samples, and then we create a cell line and isolate DNA from the blood that you send. Medical records are continuously arriving from new participants and from all of you. Thank you so much for sending new records. One thing you might do is every year on the birthday of your child with a chromosome 18 abnormality, stop and ask yourself, have I sent in records lately, and what important things have happened that we've learned in the last year that I need to send them records for? So we collect the medical records. Mimi Hasse goes through all those. She scans them. So we have saved them all the copies, but she also puts all that information in a database. Bridget Swallows, our psychometrist, she sends out lots of surveys asking for information about developmental history, etc. We also do DNA analysis in the lab, which has been on hold for the last few years because we haven't had the funding to do it. We do a little bit when it's critical, but we're way behind in that because we haven't had sufficient funding. We also do clinical evaluations Sometimes those take place in San Antonio, and sometimes we ask you to see your physician to check something out and send us that information. But that's information we get, and clinical evaluations are, of course, dependent on funding and the project that requires clinical evaluation. And then all that becomes information for families, as we've already shared all the ways we get that information back to you. So far, this was before the conference. After the conference, we probably have about 700 individuals with chromosome 18 abnormalities enrolled. This is an astonishing number. It's a lot to keep up with, but these are the kind of numbers it takes to really learn something with any confidence about these conditions, especially because there's so much variability between any group of people with these conditions. Here's where they come from. They come from all over the world, mostly North America. The limiting factor is really the ability to speak English, because in order to participate in the study, you need to be able to read and understand our consent forms in English. We could have them translated, but the problem is we do so much back and forth, send out surveys, answer questions, and having that available in many languages is really difficult. Spanish we can do, but other languages are difficult. So as far as enrollment, mostly is people from English-speaking countries or people who speak English. And just as a reminder, the people that you probably hear from directly or you may be in contact with are Courtney Siebold, who's our genetic counselor. She's the one who will answer a lot of questions. Bridget Swallow is a psychometrist, so she sends out a lot of the surveys. She's the one who keeps up the medication list. That's always very helpful for us to know what medications your child is on. And it helps us know if they're on a seizure medication and we don't have any information they've ever had a seizure. That tells us we need to ask you about sending us some information about that. Annis Hill is the project manager, and she's the one who's mostly in contact with people as they're enrolling and getting medical records. She collects pictures of everybody, which I have to say she is so proud of. They're all on bulletin boards in the hallway, and we're happy and excited to show them off to people who come through. We do tours once a month, so we get to show off all those great pictures very often, and we love it. The primary person to contact is Annis Hill, and she will, if you have a question for myself or Dr. Hale or any other member of the team, she'll route that question to them and bug them until they answer the question. We do help people come here to see some of the specialists. Depends what you need, what your questions are, but you need to go through Annis to do that, and we'll make recommendations. This is at your own expense, unfortunately, because we don't have funding to bring people in. So your insurance would have to cover the doctor visits, and you would have to pay for travel and lodging, but we'll help you with that. And the reports afterwards would, of course, go back to your doctor because you're seeing these individuals, these investigators, not as investigators, but as a consulting physician. So we can help with that. And just a reminder, if we don't do this, it's just not going to get done because nobody else is interested. So that's why it's so important to you, because we're the only ones out there doing any of this work. And again, just as a reminder, here's Annis's email address. If you contact Annis, she'll make sure that whoever your question is for will get that question, and then part of her job is to bug them until they answer the question. And sometimes that takes lots of bugging because these are people with very busy schedules, but we'll try to get your answer or your question answered as best we can. And thank you so much for listening. Thank you so much for caring, and stay tuned for exciting things to come. Thank you.